All right, so let's bring out our next finalist, Rohan Wagh from Portland, Oregon. Let's give him a round of applause. You all ready to go?
Yeah.
All right, have fun.
Hello, my name is Rohan Wagh, and I developed Motricity. On my last trip to India, I saw firsthand the struggles that people in developing regions face every day. I saw people without proper lighting, using unsafe fires and oil candles. This experience inspired me to help solve the problem of light poverty in this world. Over 1.1 billion people don't have access to reliable sources of light, something that we take for granted in first world countries. Most solutions for this problem are expensive, high maintenance, and require lots of safety precautions, all things that prove to be difficult in developing regions. That's why I believe that one solution is looking very strong: microbial fuel cells. These are a reliable and easy-to-find source of electricity, bacteria. But before I get ahead of myself, what is a fuel cell? A fuel cell is a source of electricity where two or more substances are separated into two chambers, called the anode and the cathode, that are split by a semi-permeable membrane. The flow of electrons from the anode to the cathode generates electricity. Fuel cells today have the unique ability to constantly generate electricity as long as the inputs are being constantly supplied. However, many fuel cells also use high-pressured gases, which are unsafe if not properly stored and used. That's why I believe that my cell would be the perfect solution to this problem. My fuel cell is a microbial fuel cell, a fuel cell that uses bacteria in the anode. I started out by researching the fundamentals of microbial fuel cells, or MFCs. A microbial fuel cell takes electrogenic bacteria that convert glucose and water into carbon dioxide, hydrogen ions, and electrons. These electrons then travel through a wire, creating electricity. I wanted to make a fuel cell that was durable, portable, low cost, low maintenance, and produced over 1 volt and 0.5 amps. Before building my prototypes, I decided to research the bacteria that I used. I used Shionella spp and Geobacter, which are electrogenic and anaerobic bacteria. This means that they do not need oxygen to survive and that they produce electrons through their natural metabolism. These bacteria also have small structures called nanocables, which allow them to transfer their electrons to their neighboring bacteria. This creates a grid-like structure between all the bacteria in my cell. My first cell used a Porax membrane and also used pond water, but only produced 0.07 volts. Now, I knew I had to get a better power, so I decided to first research into ion conductivity. Ion conductivity is the movement of ions from one site to another, or in my case, from one side of the membrane to the other. If I could increase the flow of hydrogen ions through my cell, I could also increase the flow of electrons through the wire, generating a higher power. I looked into lots of different membranes and chose the Cation-type membrane, Nafion, for its high ion conductivity and durability. I also wanted to find a way to increase the contact between the electrodes and the bacterium. To do this, I looked and found 3M copper tape. The copper tape allowed me to create a copper coating around the walls of the cell. This generated my second prototype. My second prototype produced 0.25 volts. That was an extremely promising result. I knew I could only get better. I still needed to find a way to increase the current of my cell. To do this, I found 3M carbon platinum catalyst. The increased carbon content in the catalyst allows for increased bacterial growth and electron and hydrogen production, while the increased platinum inside of the catalyst helps to increase the speed of hydrogen diffusion. Lastly, I decided to revisit the cathodic redox reaction, which is the reaction that occurs in the cathode of the cell. It states that hydrogen ions and electrons coming through the cell bond with oxygen gas to form water. I knew since air has a higher concentration of oxygen gas than water, if I could replace the water inside of the cathode with air, I could produce a higher voltage and current. All of these design changes culminated into my third and final prototype. My final prototype produced 1.55 volts and 0.7 amps. My fuel cell is more portable, durable, and has a higher current than existing biocells, and is even comparable to many batteries. As you can see by the graphs over here, my fuel cell has an average of 5 hours of charge, after which it has 3 hours of use. After the 3 hours of use, the total charging time decreases to 30 minutes. My microbial fuel cell is one of the first microbial fuel cells to use a carbon platinum catalyst, introduce a wall-based electrode, and experiment with using an open-air cathode. As I stated earlier, we are forgetting about the 1/7 of the population that is lacking electricity, as they are forced to work in the hours of sunlight to use rudimentary sources of light such as candles. I feel that my microbial fuel cell can be directly applied in these developing regions to serve as a source of light and energy. It can also be used by disaster relief agencies as a source of light after natural disasters. As Thomas Edison once said, we cannot solve a problem without first turning on the lights. I'd like to thank 3M and Discovery Education for this amazing opportunity, my mentor, Dr. Daly, for always helping me on my journey. my parents for always supporting me, the judges and audience for your time, and also Dr. Moran for stepping in the shoes of Mary Daly, who's unfortunately not able to be here today. Thank you very much for listening.
Did you consider any of the bacterial sources, and how would that affect your output?
So I wanted to make my design use bacteria that were locally sourced from my region, because that would really be applicable in third world countries where outsourcing the bacteria would not be an option. So many bacteria that are in a region that has high water content and high humidity are electrogenic. And so this culminates in regions that are in Central Africa, South America, and Central Lower Asia. And so I really didn't want to have to do anything special with the bacteria, because I really wanted my innovation to be able to be applied in places where they don't have the resources needed to get different types of bacteria and really study what they are. So.
Thank you, Rohan. Tell me, what did you learn from your mentor during this entire process?
My mentor taught me not to give up, especially after my first prototype. It didn't work. It didn't really produce that much, and I really felt bad, and I wasn't really sure if I should switch my project. But she really inspired me to keep working and not to give up on my cell, and it really paid off.
This is some fantastic results. Power is often compared on watts per kilogram or watts per dollar. Could you comment on where your device fits against other batteries and solar power?
Yeah, so I compared my cell to different batteries, and the cost of my cell, if mass produced, would be around 50 cents to $1, and the total watt-hour production of my cell is around 1,600 watt-hours, 1,800, watt-hours. And so I did a cost efficiency graph, which shows the cost efficiency of my cell in milliamp hours over dollars. And so it's much higher than existing batteries.
Great job. Were you able to address any of the possible unintended consequences with using bacteria as a fuel source?
Yeah, so bacteria can have a lot of consequences with using them, such as them running out of the food source, which is glucose. And so the way I'd address this is by looking at studies produced by THPRD, which is a local society, and that both takes up the parks and recs and does lots of research on bacteria in the local areas. And so I'd read on their website about how they had researched the bacteria and how they really function. And so one thing I found is that if they have a low percentage of glucose in their environment, they start to produce less hydrogen ions and electrons. So to fix this problem, I decided that if I could find some sort of source of glucose to aid the bacteria, such as crushed up leaf matter, which is what I used, then they could produce a higher rate of of electrons and hydrogen ions.
Great work. What are your next steps in your spare time? What are you going to?
I really want to expand my project to be directly applied in sewage treatment facilities and in swamps to serve as energy harvesting, and in places where the bacteria that are found are not as safe, so that you don't have to handle the bacteria physically. Instead, you can just place it inside of the swamp directly.
How is the device, say, disposed of? So once I've used it and maybe I don't need it anymore, is it recyclable, or can I do something afterward?
So the cell was not designed to be recyclable, since it does not work like a battery, as in it's the one-time use. After you disconnect it from the load, it recharges naturally due to the bacteria constantly producing electrons. So my goal was to build something that could just be constantly working. And if there happens to be a design problem with the bacteria inside, they just have to be easily refilled by opening the cap and taking them out, and then just refilling it with the same pond water that was used.
Awesome project. I like it a lot. You touched earlier on resources in developing countries. So as far as simplicity goes, if this device were to break, what do you see as precautions people can take to prevent it from breaking? And how in a developing country would they repair it?
So I was thinking my cell is extremely portable and durable, so it doesn't break easily. But if it does happen to break, mostly working with companies such as Red Cross, who do humanitarian aid, to provide stations where they can trade it out for a new cell. That would be the.
Great work. One thing you did highlight was that this system actually is using a platinum-based catalyst, and I think, as you know, platinum is, number one, a rather costly metal. And so the question I have is, number one, did you factor that into your cost calculations? And then number two, what about the robustness of your system using this approach?
So the catalyst that I got has 95% carbon and 5% platinum, and also the amount I used was very low. It was not even registered to a gram. So I used a very low amount so that there wouldn't be a high cost of platinum, and so and you said the robustness of using a catalyst. So the platinum catalysts are used frequently in polymer electron membrane fuel cells, which is a different type that has a similar calculations and similar equations, and so it's commonly used there and has extremely.
We're going to have you head out that way. Great job. All right, so we have just a couple finalists yet to present, so while we get set up, I actually want to take this opportunity and bring down a couple of our mentors and hear from them. So Dr. Done Demirgos and Margot Matera, if you guys wouldn't mind joining me. A couple microphones here. Thank you. For you. And for you, why don't we just go like that? They have plenty of room. So the interesting thing about this is like the students are up here presenting in front of the world and all of you, and when we said to the mentors, like, hey, we want to bring you down, and like these are brilliant scientists who have probably 100 patents, and they're like, what? You want to bring us down? I'm like, it'll be 30 seconds, I promise, it won't be that painful. So,
Twist your arm.
Tell us what surprised you about this experience working with your mentee.
Oh, she has been amazing and fun, and what I learned a lot about Amelia is that she's not only a great scientist, she's also an amazing musician. She's a one-person band, basically. She plays a piano, she plays a drum, and everything. And also, she's a science fiction writer. So she has multi-dimensions, and it has been, very surprising for me that a scientist can be a writer and a musician as well. So that's a plus.
Excellent.
I think our mentors were talking together at the table, and all of them either played an instrument or did a sport or did all of these, and we were talking about what kind of poetry and stuff that they like to write. So it was amazing.
I know every year I come to this and I hear like, wow, they're brilliant scientists and musicians and professional athletes, and I'm like, I can read off an iPad.
We can
Sort of,
we
right?
can even ask in the audience how many scientists are.
Yeah, of the scientists that are here, how many of you play a sport or play an instrument, right? So multi-dimensional, right? It really has. And I think we see that story with them. They're also great communicators, and they're nice kids. Memorable moments for each of you this year. You want to go first?
Yeah. So a memorable moment for me was one of the first times that I met Manasa. We were talking through her idea, and she had started with just the piezoelectric material and kind of saw some limitations with it, and she wasn't sure if she wanted to go to a new idea. I was like, well, what might you do? And she had just like buckets of ideas of things that she could work on. She's like, how about this and this? And I'm like, you just are this wealth of information and really looking to solve some challenging problems that really affect people. So I was so impressed and just continually impressed by the quality of the mentee.
Excellent.
I can just echo that, and it has been really amazing learning that she can quickly grasp everything and go and apply and come back and then even expand what she learned and teach me. And I think it has been great that she's so quick and she's great and she's a great scientist.
Excellent. Well, thank you guys enough. I said it earlier, but really, you guys are the most unique part of this. We have amazing kids, but this whole mentor-mentee relationship is really what makes the Young Scientist Challenge so special. So thank you.
Thank you.